Alright, so now we're going to start on the material for Chapter 7, which is about climate change. So you guys should remember at the beginning of the Chapter 7 PowerPoint in class, we gave you guys the example of that kind of Viking colony in Greenland that arrived during the Middle Ages around the 1100s and 1200s. And by the 1300s and 1400s, the climate there had cooled to the point where those people were no longer able to grow crops and sustain themselves. So those people all moved back to Denmark or whatever parts of Scandinavia they were from. And that's just another example how the climate has constantly been fluctuating through all of human history. I gave you guys the example of the Roman Empire, how the Roman Empire rose to their greatest power during a time when the climate in the Mediterranean world was very warm. And then as there was a shift in that and the climate got very much colder, it drove a lot of people from Northern Europe into the Roman Empire, and it eventually destabilized the whole thing to the point where the Western Roman Empire completely collapsed in the 5th century. And even as far back as 3,000 years ago, we think that the Mycenaean civilization in ancient Greece collapsed in part due to a significant climate change event, possibly caused by a volcanic eruption off the coast of Greece, because around 3,000 years ago, a very powerful civilization just completely disappeared, and Greece entered a period of dark ages where the civilization was very unstable. So throughout the course of history, climate and human beings have been intertwined, and we're very dependent upon our relationship with our climate to grow crops and to maintain stable, healthy human settlements. Two climate eras, small climate eras that we talked about in class are first the medieval warm period, which was a naturally warm period in Europe from about the year 950 to about 1250. So this is when Europe emerged from the Dark Ages after the fall of the Roman Empire, and we see large, stable kingdoms begin to form again. And a big part of the reason why that happened was this warming of the climate that allowed us to grow crops in large quantities again and allowed European civilizations to start building big cities again for the first time since the fall of the Roman Empire. Immediately after that medieval warm period, we had a period of significant cooling called the Little Ice Age, which lasted from around 1350 to about 1850. So we had a period of about 500 years where the Earth got significantly cooler after that medieval warming period. And now we believe we're in another kind of miniature warming period again after the Little Ice Age. So this just shows that the climate is constantly fluctuating, and it always has from the beginning of time, millions of years ago. Sort of like a Russian nesting doll picture, that there are constant trends of warming and cooling that fluctuate within each other. So first we'll define climate versus weather, because it's a very important distinction and you need to know the distinction for your exam. So climate is the long-term average of weather and the average frequency of extreme weather events at a given location. Whereas weather is just the state of the atmosphere at any given moment. So climate is the long-term average over many, many years of weather and the average frequency of extreme weather events. So for us to consider that the climate has changed, the weather patterns have to maintain that trend over many, many years first before we can accept it as a climate trend rather than just a random anomaly or fluctuation in the climate pattern, which do happen. So energy and matter move through the Earth's systems to form our climate system, as the Earth is constantly fluctuating, trying to maintain an equilibrium of its energy. Over time, this forms the climate system. So climate change occurs only when the long-term average of any meteorological variable, such as temperature or precipitation, changes. So again, random one-time events are not considered climate change. There has to be a sustained long-term trend that changes a weather event. So individual extreme weather events, such as a huge volcano eruption like Krakatoa, does not change the long-term average. It might affect the climate of Earth for a couple of years, but then things will eventually revert back to normal. Climate change is a sustained pattern of change in any variable over a very long period of time, such as the temperature or an increase or decrease in the precipitation of an area. So a climate forcing factor is a force that can change the climate and is unaffected by the climate system itself. The most common form of this is solar forcing. So an increase or decrease in solar activity may have an impact on the climate and cause climate change. Whereas a climate feedback occurs within the climate system itself, and it either enhances or diminishes climate change that has already been set in motion. And the most common example of this is the ice albedo feedback that we talked about in class. So currently, as the ice caps melt, that creates a climate feedback where the melted water absorbs more sunlight in that area and causes even more ice to melt, which further changes the climate. And the opposite, of course, happens if the ice were to cool and there were to be more ice. That would increase the reflectiveness of that ice, and it would cause the climate to cool. So it works both ways. That's an example of the climate feedback. It's happening within the climate system itself, whereas a climate forcing factor occurs independent of the climate system and is due to an outside force like the sun in particular. There are three natural modes of climate change. There are long-term trends that happen over millions and millions of years. There are repeating cycles that happen in regular intervals over tens of thousands of years. And there are random anomalies that can last anywhere from a very small period of time, like a couple of days, to many, many years, depending on the length. So I gave you all the kind of Russian nesting doll example earlier. That's kind of how I like to think of the modes of climate change, because the random anomalies happen within the repeating cycles, and the repeating cycles happen within the long-term trends. So there are many, many fluctuations that are all happening at the same time. There's a good graph on page 203 of your textbook in chapter 7 that does a good job of illustrating what I just talked about, how those shorter trends are wrapped within the longer trends of the climate. And again, these changes to the climate, whether they're short-term or long-term, are caused by climate forcing factors and the climate feedbacks that we talked about earlier. So we'll start with the very, very long-term trend that's been lasting about 55 million years at this point, called the Cenozoic cooling trend. And all that means is that the atmospheric temperature has dropped steadily since the early Cenozoic era, about 55 to 60 million years ago, right after the dinosaurs died out. So this cooling trend began when India, the subcontinent, collided with Asia, forming what we now know as the Himalayas and the mountains of the Tibetan Plateau. That event caused the overall atmospheric temperature of the Earth to drop significantly over the past 55 million years or so. In fact, the climate 55 million years ago was about 22 degrees Fahrenheit hotter on average than it is today. So it was a completely different climate. There was no ice anywhere on Earth at all. And of course, we had completely different plant and animal species that lived on the Earth that are now extinct because the climate changed so significantly from that time. Now, next we have climate cycles, which occur over a much shorter time than the trends, the much longer term trends do that last millions of years. So over the last 1 million years, glacial climate cycles have lasted about 90,000 years, and interglacial periods have lasted about 10,000 years. And those fluctuate back and forth over the last million years or so. So currently, we're in an interglacial period called the Holocene, which has unusually stable climate. This period began about 10,000 years ago, and it's no coincidence that the first kind of modern human settlements and civilizations that are still around today began about 10,000 years ago. It's about 10,000 years ago when we see the first human settlements form in Asia and the Middle East, and then gradually human settlements have expanded all over the world to where they are today. But before about 10,000 years ago, there's really no evidence of human beings living in the organized civilizations that we have today. About 10,000 years ago is when humans first figured out how to domesticate crops and also domesticate animals, which are really important for the development of human civilizations throughout history. So our current interglacial period, the Holocene, began right as the last ice age ended. And our reminders of that are that many of the glaciers that used to entirely cover most of the North American continent, as those glaciers melted and moved, they tremendously scarred the landscape, and we could still see the remnants of that even 10,000 years later after those glaciers melted and moved around as the Ice Age came to an end. So related to the glacial and interglacial periods I just talked about are the Milankovitch cycles. These are small changes in the Earth and Sun's orbital geometry that result in quaternary glacial and interglacial cycles. And that makes sense. How far the Earth is from the Sun has a huge impact on our climate, and even a small change in that geometric relationship will have tremendous effects on our climate. So these Milankovitch cycles, these changes in the Earth-Sun orbital geometry, this is another example of a climate forcing factor because it's happening independent of the Earth's natural climate system. It's because of an outside force, but those changes do cause also internal feedbacks, which do happen within the climate system itself. So the two are interrelated. And also things like volcanic eruptions can cause short-term cooling by injecting ash and sulfur dioxide into the atmosphere to the point where they block out a lot of the sun's rays and can cause global cooling for a very short period of time. And lastly, we have things called climate anomalies that occur randomly. So changes in the sun's output, changes in the ocean conveyor belt, and volcanic eruptions. These are climate anomalies that occur randomly, and they generally have relatively short-term effects on the climate and are unpredictable. Scientists think that low sunspot activity may have triggered the start of the Little Ice Age, and relatively high sunspot activity may have triggered the medieval warm period. So even though these things seem to occur randomly and unpredictably, they do have a small impact on the climate, even though they're not long-term, predictable, sustainable models of climate change. They do have an impact. One last example of how the climate can have unpredictable effects is called the Younger Dryas. So basically, 12,000 years ago, there was still a large ice sheet over North America called the Laurentide Ice Sheet, and as the climate warmed and that ice sheet gradually melted, an impact of that melting down the line was that all that extra water into the ocean actually slowed down that ocean conveyor belt system that warms the climate. So because all of that extra water was in the ocean, it slowed down the conveyor belt enough to have a global cooling effect for about 1,000 years at the very end of the last ice age. So the Younger Dryas was a cold period in most of the northern hemisphere between about 12,900 and 11,600 years ago. That was really the last fight that the ice age put up before finally the gradual warming trend of the climate took over, and we've had a consistently warming trend in the climate ever since. But the Younger Dryas was sort of a brief period where the climate trend went against what had been the prevailing trend for most of the previous many thousands of years by having a cold period. And only after that Younger Dryas period ended do we start to see human settlements begin to form over the next couple thousand years. Because previously it had been too cold for vegetation to sustain itself because of this Younger Dryas period. Now we'll move on to talking about the carbon cycle. So the carbon cycle is the natural transfer of carbon dioxide between the lithosphere, which is the surface of the Earth, the crust, and the atmosphere in the air. So over the last 800,000 years, natural atmospheric carbon dioxide concentrations have changed very little because there's been a balance between the amount of carbon that has entered the atmosphere and the amount that has left the atmosphere. It's only in the last 200 years or so, because of the Industrial Revolution, that we've started to see this balance become unbalanced. So in the last 200 years, human activity has greatly accelerated the transfer of carbon from the lithosphere into the atmosphere, about 35 billion metric tons each year. So we're putting a lot more into the atmosphere than what is naturally returning back to the lithosphere. We've thrown that natural cycle out of balance in the last 200 years. So the leading causes of this acceleration in atmospheric carbon dioxide are the burning of fossil fuels as we've industrialized our human societies, but also deforestation. So you probably learned in your biology classes in high school and maybe here at LSU that trees absorb carbon dioxide as part of their photosynthesis process. Well, as we burn trees, there are less of them around to absorb the carbon dioxide that is naturally in the atmosphere. So it just stays there. And that's having a lot of effects over the last 200 years on our climate. Before 200 years ago, we believe natural carbon dioxide concentrations had never surpassed 300 parts per million, but now the carbon in the atmosphere is over 400 parts per million, and it's gradually increasing with each year, we think due to human activity heavily. And possibly as a result of this change, atmospheric temperatures are slowly rising because of the carbon greenhouse effect that we'll talk about later. Scientists and geologists use a special type of graph called a Keeling curve to show the change in atmospheric carbon dioxide concentrations since 1958, when we've really gotten accurate, up-to-date global measurements for this. And there's a good example of what a Keeling curve looks like at the top left of page 212 of your textbook. So now we'll talk about the anthropogenic greenhouse effect. And anthropogenic is just the fancy Latin word for man-made, essentially. So the anthropogenic greenhouse effect essentially is that human increased emissions of carbon dioxide and other greenhouse gases are creating a man-made greenhouse effect that enhances the natural greenhouse effect and is changing the nature of the atmosphere. So there is a naturally occurring greenhouse effect, but over the last 200 years, as we've put more and more carbon into the atmosphere, it's increased this natural effect, and it's begun to destabilize the climate and cause all sorts of changes. So the area that our greenhouse effect is impacting the most by far is the Arctic. The ice albedo positive feedback is warming the Arctic at about twice the rate of the rest of the world, and that's part of why a tremendous amount of ice is melting there each year, because we've enhanced the natural warming effect there, and as more ice continues to melt, it creates a feedback loop that melts even more ice because it absorbs more heat due to the melted water, and it melts the residual ice as well. So the average atmospheric temperature of the Earth is higher than at any point in the last 1,500 years. So really, since the fall of the Western Roman Empire, I talked about that earlier, this is the hottest that the Earth has been since that time. There's, of course, a lot of research being done about this, but as of now, no known natural climate forcing factor can explain the current warming trend that we see in the atmosphere. So the most likely explanation is that our man-made activities that are putting more carbon dioxide into the atmosphere are heavily responsible for this warming trend we've seen in the last 200 years. And the reason it's been about 200 years is because that's about how long that we've been burning fossil fuels on a wide scale. So the use of burning coal for fuel on a wide scale was first developed in Britain about 200 years ago, and gradually that technology has spread all over the rest of the world. And we don't use it only for coal, we use it to create gas, we use other types of greenhouse gases like methane to cook. So as the technology has expanded further and as the human population has grown tremendously in the last 200 years, we see this greenhouse warming effect take off significantly over that time. So most scientists believe that if we can limit the atmospheric carbon dioxide to less than 500 parts per million, we can avoid significant climate change in the long term. Remember, right now, we're roughly in the 400s parts per million, whereas before 200 years ago, we think the natural carbon dioxide in the atmosphere had never surpassed 300 million. So right now, our goal is to keep our level below 500 parts per million. So that's why over the past 50 years especially, we've seen tremendous efforts, especially in the Western world, to try and limit our carbon footprint. We define our carbon footprint as the amount of greenhouse gases, especially carbon dioxide, that any activity generates. So we're trying to develop more energy efficient means that produce much less carbon emissions and reduce the effect that that has on the atmosphere as a result. So we're trying to put more emphasis on solar energy, wind energy, any type of energy efficient process that doesn't emit lots of carbon dioxide or other greenhouse gases into the atmosphere so that the atmosphere can recover itself over time. And our final note for chapter 7 is that climatologists use Earth system models to develop predictions about how climate might respond to greenhouse gas forcings. So it's a model that attempts to predict in the future how certain carbon levels will have an impact on the climate. That wraps up our notes for the chapter 7 material. We'll conclude the exam 3 review with the material for chapter 9 in the next video.